Today on Astronomy Toronto, we'll discuss variable stars and take a look at Toronto from a vantage point out in space. Hello again. Welcome to Astronomy Toronto. I'm your host. My name is Randy Attwood, and I'm a member of the Toronto Centre of the Royal Astronomical Society of Canada. Well, today we're going to be talking about variable stars. That's our topic. We'll meet our guest in a moment, but before we do that, I thought we'd show you a film of what you'd see if you were orbiting the Earth above Toronto during the winter. Now, we've all seen pictures of the Earth taken from space by satellites or by astronauts, but I doubt you've ever seen, say, Ontario when it's covered with snow. This film that we're going to roll now is it was taken 14 years ago by the Skylab astronauts, and it is from an altitude of 270 miles. Remember, the Skylab space station was put in orbit to hold 3 men for periods of months, and they got a view of the Earth as they rotated once every 90 minutes. This tape you'll see will actually go over the Great Lakes and seen in wintertime. What we'll be seeing is first Lake Michigan as we're coming over at 270 miles, and then we'll actually see Lake Erie and Lake Ontario. All right, so here we are in orbit. There's Lake Michigan just approaching, and if you could see Chicago down at the bottom of your screen, a lot of ice, a lot of water. Now we're coming up over, well, who knows what that is, a lot of snow. There's Lake Huron, and now we're coming up on Lake Ontario. There's Lake Erie at the bottom and Lake Ontario, so we're tilted 90 degrees. So wave, that's Toronto down there, just on the left. So it's very interesting. One thing it does mean is that at wintertime the Earth looks a lot brighter from space because the light is reflected more. Well, enough about that. Let's talk about variable stars. My guest today is Dr. John Percy. He's an astronomer at the University of Toronto. And John, you would be classified as a variable star astronomer.
That's right.
Thanks very much for coming on Astronomy Toronto today.
It's my pleasure.
Tell me, what is a variable star?
Well, a variable star is any star that varies in brightness. And we tend to describe them by means of these graphs like this.
Mm-hmm.
This is called a light curve, and it represents the changing brightness of the star with time. So the one on the top here rises very rapidly, and then over the course of many days it gradually fades away. This is the kind of light curve you get from what we call a nova.
Mm-hmm.
The one down here, the brightness falls and rises and falls and rises in a regular kind of way over a few days, and an example of that would be a pulsating star, and there's many of these in the sky.
All right, so there's different types. Could you show us why stars vary?
Okay.
You got some models here?
Sure, I have, and let me take a simple example here. Here's a star which has a big spot on it, and the star turns on its axis as the sun does, and you'll notice that when the spot is turned towards you, the star should appear fainter, and when the spot is turned away from you, the star would appear brighter. So that's a very simple kind there. Let me show you a slightly more complicated one here. And this is a variable star that consists of 2 stars. So this is an example of a binary star. And these 2 stars are going to go in orbit around each other. And you'll notice that every now and then one of the stars gets in front of the other star and eclipses it.
Mm-hmm.
And every time one of those eclipses took place, then the combined light of the 2 stars would get fainter. There's a very useful kind of variable star. Those 2 are strictly geometrical. It depends on you being in the right position to see the effect. Then there's some other stars that are more physical variable, and so one of the most interesting is a pulsating variable star. I'm going to show you this with this balloon here. This is a red giant balloon, by the way, and its name is Charlie Brown. And one of the things this balloon does is to illustrate the balance that exists in stars. And in stars, gravity pulls the star inward, and the pressure of the hot gas inside pushes the star outward, and everything is in a nice balance. Now, this star here, it's really a star, there's gas inside it that's pushing outwards, and it's the tension of the rubber in the balloon that pulls inwards and balances that. So right now this balloon is in balance, but if I increase the pressure inside, it would expand, and if I released it, it would contract. And a pulsating star is one that expands and contracts in a regular way. Now, I can actually use this balloon for something else as well, to show you something about pulsation or vibration. And that is that you would probably all try to do this little experiment. You take the balloon and you do this. And so in this case, the pressure or the force of my hand pushes the balloon outward, and at the same time the elastic pulls it inwards, and so I get a nice vibration. Now, if I make the string longer here, then the vibration slows down. And if I make it as long as I can, then the vibration is even slower. And this is something that's generally true of pulsating stars. The bigger they are, the slower they pulsate. Now, the fourth kind of variable star is what we call an erupting or exploding variable, and I could demonstrate that quite easily by taking this pin here and sticking it in the balloon and destroying the balance that exists between the inward pull and the outward push. I won't do that because it would probably break our microphone, but there's an example of it there. Actually, I could illustrate some of these things also by showing you a few slides. So maybe we'll take a look at some slides that will show you something about different kinds of variable stars.
Our first slide is our sun.
That's right.
That's not a variable star, is it?
Well, you'll notice it has spots on it, and the sun turns on its axis, so if you saw the sun from a long distance away, it would vary with the same period or cycle as its rotation. And in fact, we can study other sun-like stars at a distance in the same way and find out whether they have spots or whether they turn on their axis. Now, let me show you another slide that illustrates one of these eclipsing variable stars. And the name of this is Algol. It's one of the most famous of variable stars. And you'll notice its light curve there. And the star decreases very rapidly in brightness where it says 0 hours there. And that's because a large, fainter star gets in front of a smaller, brighter one. And then when the large, faint one gets out of the way, the star goes back up to its normal brightness, and then 69 hours later, the big faint star gets in front of the bright one again, and we get another eclipse.
So that's one of those physical ones we were
Yeah, this is one of the eclipsing variables, and anybody can see it with their unaided eye, as long as they know when to look.
Now, if one of those orbiting ones was tilted, if one didn't happened to pass...
You wouldn't see anything.
We wouldn't see a variable.
No, we wouldn't see a variable star.
But we can't see, when we look through a telescope, we can't see those two individual stars.
These are generally too far away to see that there's two stars there. It's very rare for them to be far enough apart so that you can see.
Okay, so we just see the increase, decrease over a period of time.
That's right.
And through other methods we can tell that there are two.
That's right. So you can tell there's two stars there even though you can't see them, because you can see the effect of the one star on the other.
Okay.
Now let me show you another slide that shows one of the other kinds of variable stars, and that's the pulsating variable. This is a light curve now for Delta Cephei, another famous variable star, and you notice that the brightness goes up, and then it goes down, then it goes up. And along the bottom there is represented the fact that this star expands and contracts and expands, and at the same time it changes temperature, and when it's yellow there it's brightest, and when it's an orangish color it's the coolest. And so it's a combination of these changes in color or temperature and the changes in the size of the star that cause it to vary. It's a physical effect.
How often would it take? How long would it take to expand?
Well, for this star it takes about 5 days, but some of these Cepheids are so big that it takes 100 days for them to go through one of their cycles.
And this is constant over time?
More or less, yes. There's a slow change in the period which you can actually detect if you time it regularly over many years. And this change is due to the slow evolution of the star. And this, in fact, is one of the kinds of projects that that amateur astronomers can do with small telescopes. So anyway, these are Cepheid variables. Let me show you now some slides of some of the erupting variables, or in some cases actually exploding variables. This is a set of 3 images of what's called a flare star. Now if you look at the star that's at the very top there on the left, there's a series of 3 images, and they're taken just a few minutes apart, and they increase in time from the right to the left. And you notice the very top star and the last exposure there is becoming much brighter. That's a star that flares up within actually a few seconds. Very much like the sun occasionally flares, but the sun flares in a much more modest way. But some of these flare stars, they can change brightness by a factor of 10 or perhaps more, just within a few seconds. That's a fairly modest kind of eruption even there. There's other stars called novae. The next slide shows an example of what we think a nova looks like. This is kind of hard to see here because we're looking from behind one of the satellites of this reddish star that's in the foreground, and material is actually being pulled from that reddish star over to that thing in the distance there on the right, and that's an example of a white dwarf star. It's a star that's actually finished its evolution, and by pulling material over onto its surface, it can actually, after a few thousand years, kind of rejuvenate itself. It's got a new supply of fuel, and it suddenly begins to use this very rapidly, and you get a huge outburst of brightness from this star over a period of a few weeks or a few months, and we call that a nova. But the star gets rid of this extra fuel, and it goes back to its normal state. And there's one other kind of variable star, one other kind of eruptive star that is much more violent than that, and that's shown on the last of this series of slides. It's a slide of one of the most famous objects in the sky. It's called the Crab Nebula. It was observed to explode in the year 1054 AD. And this is an example of a star which has almost totally disrupted itself at the end of its lifetime, leaving only a tiny little remnant behind. This is the most colossal and violent kind of stellar event that astronomers know of. It's the ultimate variable star.
And we're all looking forward to seeing one.
That's right, yes.
Sometime soon.
Yeah.
Why are variables important to study, John?
Well, first of all, because they're just so numerous. There's something of the order of 50,000 variable stars that have already been identified, but there's probably millions out there that we just haven't got around to looking at yet. In fact, if you take this picture of the winter constellation Orion, there's a constellation that most people know. It has 4 stars around the outside, 3 stars on the belt. And I've put an arrow beside the stars that are variable, and you'll notice that 5 of the 7 stars are variable in brightness, and it just goes to show just how numerous these things are in the night sky.
And where could we see Orion tonight on February night?
Well, in the winter, it's just nicely placed up in the south in the early evening. It's an easy constellation to see. In fact, one of the brightest variables in the whole sky is this star in the upper left shoulder of Orion. It's called Betelgeuse, and it's a very red, large star, and it varies quite substantially in brightness. It varies rather irregularly, and in fact many variables vary quite irregularly and unpredictably, and that's one of the things that's interesting about them. They're kind of pathological objects, which is one of the reasons I like to study them. But from the point of view of pure astrophysics, the reason we like to study them is that they tell us something unique about the star. For instance, when I showed you this rotating variable here, you'll notice that by measuring the period of the variability, you're measuring the rotation of the star, and you're finding out that there's star spots. And in the case of the Cepheid pulsating variables, we can actually determine the size and the brightness of the star by measuring the period or the cycle of its pulsation. So variable stars are tremendously useful to the astronomer.
Well, with 50,000 variable stars, known variables out there, astronomers can't possibly look at them all.
No, and thank goodness we have the help of amateur astronomers in this respect. With a small telescope, you can monitor these stars, and particularly in the case of the irregular and the unpredictable ones, we just don't have time to go out and watch every night for something to happen. And there are thousands of amateur astronomers in the world who do this as a hobby. The measurements are simple, at least there are simple measurements that one can do. Then as you get more accustomed to doing this, then there's more advanced kinds of activities that can be done.
So astronomy is really a unique science where amateurs can contribute to the science.
It really is, yes.
All right, that's interesting. Let's talk about different ways of observing variables. I guess the easiest way is to go out and look in the sky with your naked eye.
That's right. Just use your eyeball, and that's the way it was done for thousands of years. Oriental astronomers started observing variable stars way before the birth of Christ, and this was the way it was done until the late 1800s, when photography was developed. And there was one particular individual who figures very strongly in the history of variable stars, and I brought along a slide of this chap. So on the next slide you should see a picture of John Goodrick. He's a rather tragic figure because he was a deaf mute who died in his early 20s, but yet within his short lifetime he established the study of variable stars. He discovered some of the most important ones, and he even made hypotheses as to why these stars vary. And many of the, or most of the thousands of amateur astronomers that study variable stars still use the kind of technique that he developed. In fact, one of his discoveries was a star in the constellation Cepheus, which is called Delta Cephei. And this is the kind of chart that a visual observer would use. The variable is marked there in red, and there's a few stars on here that are constant in brightness, and their brightness is marked by means of numbers, and we call those comparison stars. And we measure the brightness of the variable star with reference to these comparison stars. And you can do this to an accuracy of about 10%, which is certainly good enough for many purposes. So this is the kind of thing that's involved in visual observing. Now, there's more advanced techniques that you can use, and I brought along a slide of a very famous Canadian astronomer who's one of the great figures in variable star observing. So we should, in the next slide, see a picture of Dr. Helen Sawyer-Hogg of the David Dunlap Observatory. And she has spent her astronomical lifetime photographing variable stars, particularly in large clusters called globular clusters. She did her work mostly at the David Dunlap Observatory, and there's a picture of this observatory in Richmond Hill. And on the next slide we see the kind of pictures that she took. There's two photographs of a globular cluster here. They're taken at different times, and you'll notice that on the left, the star with the arrow on it is much brighter than the photograph on the right. So that there's an identification of a variable star. And on each of these photographs you can measure the brightness of that. And in fact, in many of these globular clusters there's hundreds of variable stars, so it's a very efficient way of studying these objects. Now, these days we've moved most of that program of studying variable stars in globular clusters to our southern observatory in Chile. That's shown on the next slide. It's a location in the Andes in Chile.
Why put a telescope in Chile, John?
Well, several reasons. One is that you can see the southern part of the sky that we can't see here, and most of the globular clusters are actually in the southern part of the sky. The other reason is that the sky is darker, it's clearer, it's steadier, and for many purposes that's something that we would like to have. So anyway, that's one way you can study variable stars. The third way is kind of a more sophisticated way, and that's using photoelectric photometry. On the next slide you'll see a picture of one of our smaller telescopes at the Dunlap Observatory, and that white thing on the right-hand side there is a photoelectric photometer. It has a sensitive electronic tube in it, something like the light meter on a camera, and that white vertical box there is a set of color filters that you can use to measure the color of the star as well as its brightness. And this is a picture of how you put the photometer at the focus of the telescope, and on the next slide we see the results of doing that kind of measurement. The next slide is the light curve of a variable star. That up and down change in brightness is only 10% change in it's only 2% change in brightness, and it takes place over a period of about 45 minutes. This is an example of a very fast pulsating variable, and one which doesn't change very much. You could only measure that using a photoelectric photometer.
Very, very accurate.
Very accurate, yes. And actually even amateurs can do this kind of work now, because you can buy a photoelectric photometer for about the price of a video camera and put one on the back of a small telescope, and you can do some real astronomical research.
Tell me about the amateur variable star observing organization.
Well, if you are really interested in getting into this kind of activity, then I'd strongly recommend that anyone join the American Association of Variable Star Observers. Now, although it says American, it's an international organization, has members in something like 45 different countries of the world, and there's something of the order of 1,300 members. It's an old and distinguished organization that was founded over 75 years ago at the Harvard College Observatory because the astronomers there realized that they were going to need help in observing variable stars. And the AAVSO, as we call it, has been observing these ever since. It's now recorded over 5 million observations of variable stars. All of these are archived in machine-readable form at their headquarters in Cambridge, Massachusetts. So these observations are available now to professional astronomers for their work.
And so you've called down to their
I use
library?
their data quite regularly because it enables us to, for instance, study the long-term behavior of variable stars. Their observations actually go back before 1911, before the time that it was formally established. And, you know, one of the things that I find remarkable about the AAVSO and visual observing is that with the coming of the space age in the last 10 years or so, it turns out that their observations, the visual observations, are actually more important and more valuable than they were before that time. And let me give you an example. Some of the astronomical satellites are used to monitor these exploding stars like novae and their relatives, but you never know when these things are going to explode. And so if an astronomer is using one of these satellites, then he arranges with the AAVSO visual observers to monitor these stars and to immediately notify him or her as to when one of these stars erupts. And then he can turn his satellite onto this particular star and study the process of the
Watch
outburst.
it rise, possibly.
That's right, that's right. And there's been a tremendous cooperation between satellite astronomers and the visual observers of the AAVSO. Another example of something really quite revolutionary, I think, has to do with the discovery of these supernovae, these ultimate variable stars. It's been actually something like 300 years since one went off within our own galaxy and was bright enough to be recorded with the unaided eye. What we have to do now is to look for these things in distant galaxies where they're very faint. And there's actually a visual observer in Australia by the name of Robert Evans. He's a minister by profession, but at night he goes out with his telescope and he can observe 600 different galaxies in the course of a night. And as a result of this, he's discovered something like a dozen of these supernovae.
So he's got all those galaxies down to memory.
That's right. He's memorized all of these things, and it's something tremendously useful to professional astronomers to be notified of these explosions immediately, and then they can turn all of their large sophisticated telescopes on these objects and be able to study them as they're going off, so to speak.
Well, we have a variable star observer in Ontario who has made some contributions.
That's right. Actually, we have many variable star observers in Canada who have very distinguished observing records. You're probably referring to Warren Morrison, who lives up Peterborough way, who's not only discovered 2 novae, but has also made over 20,000 observations of variable stars. Extremely good observations. He's very highly regarded by the AAVSO. And there's others in Canada. There's Stephen Sharp in London. There's Chris Spratt in Victoria. There's been a number of others who over the years have made important contributions in this area.
Something I find fascinating about variable stars are a certain type, the Cepheids, the ones which vary over time. They were very important in the early part of the century, helping us to determine distances in space, weren't they?
That's right. It's because of the fact that the period of the pulsation is connected with the size of the star, because the light output of the star is also connected with its size. So if you know the period of pulsation, then it determines the size and hence the luminosity of the star. And if you compare the luminosity that you know with the brightness that you observe, you can figure out how far away the star is. And this is the basic method for determining distances within our galaxy and to the nearby galaxies. And with the Hubble Space Telescope to be launched next year, I hope, then this project is going to be expanded to even more distant galaxies. It's one of the most exciting projects that the Space Telescope will do.
variable star observing is essentially active up in Richmond Hill at the David Dunlap Observatory, isn't it?
It still is, yes. We're managing to get around the problems of light pollution and so forth. And
Well, you've had to do special, set up
yes.
some special mechanisms to...
That's right. One of the more ingenious is set up by Don Fernie, who's the director of the observatory, and he actually observes variable stars through haze and cloud by using two telescopes. One looks at the variable, one looks at a comparison star, and if there's any haze in the way, it affects both of these beams in the same way. And so he can correct for the presence of the haze or cloud or whatever and do this kind of work on a lot more nights than was previously possible.
He's got another 5,000 stars he wants to look at anyway.
That's
so he's
right. There's more than enough work to keep us all busy for a lifetime.
What is the future, well, how does the future look for variable star observers? Just systematically looking at different variables?
Well, it's hard to say. Right now, the number of variables is increasing by a factor of 100 every 100 years. So one of the problems is just going to be keeping track of them all, and that's a data handling problem to some extent. But it still requires a knowledgeable astronomer to figure out, well, what do you do first? Which of the stars should you be looking at? But there's lots to do. There's lots of unsolved problems in variable star research.
And the Hubble Space Telescope, you think, is going to add a lot?
This is going to help, but at the same time, amateurs with visual observing techniques or with photoelectric photometers, they're going to help too. And they've made some substantial contributions over the last 10 years in both the visual and the photoelectric area. And you might wonder, well, what about photographic study? Well, one of the things that I regret is that so many amateur astronomers do astrophotography, but they never actually use their photographs to do some real science with. And this is another area that they could move into if they chose to do so.
Thanks very much, John, for coming on Astronomy Today.
It's my pleasure. I'm always glad to talk about variable stars.
Well, it's a very interesting topic. And thank you very much for watching Astronomy Toronto. My name is Randy Attwood, and I'm with the Toronto Centre of the Royal Astronomical Society of Canada. If you happen to be interested in observing variable stars or just in astronomy in general, then get in touch with us, care of the McLaughlin Planetarium here in Toronto. You don't need a lot to observe variable stars. You just need some ambition, willing to go out at night, learn the stars, and possibly an observer's handbook or some variable star information which we can provide you with at the Royal Astronomical Society of Canada. During February through May, the second Sunday of every month, between 1 and 4 in the afternoon, Toronto Centre members will be at the Royal Ontario Museum to discuss astronomy with you. So until next time, Sunday, the first Sunday of every month at 9:30 here on Rogers Cable 10, we'll see you on Astronomy Toronto.